Hello everybody, welcome to Noritsu's worldwide webinar on inkjet information. I'm Ron Kubara. I'm with Noritsu Canada, based out of Vancouver, and I'm coming to you from Florida right now. The session that we're about to go through is a collection of information about inkjet technology, terminology, and comparing the different types of papers and inks that are available for photo imaging. End of the session, I'm going to talk about illumination and lighting of prints and imaging in general, as well as image capture by camera devices and the impact on illumination as well. I'm going to try to tie it all together and hopefully bring you a great deal of information in approximately 80 minutes time and allow for questions and answers, or hopefully answers, but certainly questions at the end of the session. What started my quest What started my quest for information on ink technology was the introduction of our QSS Green series. And on our QSS Green series, we brought a new feature to the market, and that was utilizing third-party sheet paper. And in utilizing third-party sheet paper, I found out there are a lot of different papers on the market. And different manufacturers use different specification numbers and information that they are providing about these papers. And it was information that I knew very little about. So I started this quest to really understand it, and in the process of understanding it, I found out that some of the information is standardized and some is not. So I'm going to go through all of that today. My main goal is to be able to provide you with a great deal of information where the vast majority of it is quite important to us in the imaging market, certainly for us as imaging professionals. There are a lot of terms such as microporous and swellable and rag and cotton, all terms that are used in the inkjet business and sometimes on the packaging itself, but certainly within the specifications. So understanding what all these terms mean are quite important. And an area I'm really going to concentrate on is this term down here, OBA, which is optical brightener agents. It is quite important to understand the product's use of OBAs and that impact on illumination of the product itself. Some of the areas I'm going to be going through are based on comments and questions I've learned as a salesperson representing Noritsu products. For example, colors don't look right on the screen as compared to the print itself. Well, an inkjet print is never going to match the look on the screen. And one of the plain simple reasons have nothing to do with the color. The paper has a much brighter white and a much deeper black than any monitor or display device in the world is going to be able to provide. So right out of the gate, inkjet has a much greater contrast range than a monitor. Now that doesn't necessarily mean that it's more contrasty. It has a greater contrast range capability. Another thing that I hear commonly said in the market is inkjet cannot reproduce skin tones as well as color. I disagree with that, and unfortunately during this webinar I'm not going to be able to hand out sample prints, but I'm going to show you images, and I'm hoping you're going to trust me that the images are a true representation of the prints that I would hand out. I have created, without a doubt, and proven to anybody who attends a session, that inkjet can match the skin tone color of silver halide prints. Another comment that I hear quite common is the output is grainy, I can see the drops. Well, I suspect there's a very strong likelihood you can't see the drops itself. The drops are very small. A person's vision can see approximately 267 dots per inch and not any greater than that. And there are much smaller dots and more dots than that in an inch in inkjet technology. What you can't really see the dots, but what you can do is you can see clumping of the dots. And I'm going to get into that in the session and explain that, hopefully clearly. And the last area I'm going to talk about is print banding, a common term that is used. Quite often it's used accurately, but sometimes it's used inaccurately. So I'm going to show the different types of bandings that occur and the causes of them. And to begin with, I'm going to start with ink. In photo imaging, we have two types of ink. We have dye ink and pigment ink. The easiest way that I use to describe dye ink and pigment ink, dye is a liquid. It's a colored liquid, whereas pigment ink is a floating particle in a solvent. It is opaque. the dye inks are translucent. And this is really quite important when you try to compare ink technologies. Dye inks do not have as good image permanence as pigment inks when exposed to light. There is no doubt that pigment inks are of the best image technology for image permanence, for print permanence. However, Noritsu dye inks have a different molecular structure than traditional dye inks, and they do have a greater image permanence than traditional silver halide paper. Please note very clearly, not all dye inks have the same permanence. On the other hand, pigment inks is much more sensitive to abrasion. If you took your finger and placed the back of your fingernail, on a pigment ink print and pressed with a little bit of pressure, you will see that your nail can cause an abrasion to the print. Not necessarily a scratch, but it can cause an abrasion. And if you look on unreflected light, you'll see the path of your fingernail. Dye inks are much less susceptible to that. Where it becomes important is when you have two prints on top of each other in a packaging scuffing each other. Pigment inks can be prone to getting scuff marks, and dye inks are much more resistant to that. Additionally, because dye inks are a solvent, the droplet size can be smaller. It can go as small as 1.5 picoliter, whereas the pigment ink smallest drop size is about 3 picoliters. So the dye inks can be much smaller as it's transmitted through the nozzle than the pigment ink. Again, the reason is the pigmented ink is a floating particle in a solvent, and the dye ink is the colored dye. So we can get to a much smaller droplet size. This translates to sharpness and finer detail. But probably the largest area of difference between pigment and dye inks is an area that's not understood very well. When somebody asks me how many colors our printer has, I don't like to immediately answer the question until explaining this. Pigment inks are opaque, and when one droplet lands on top of the other droplet, the last droplet is the color that is shown. Whereas with dye inks being translucent, just like silver halide paper, they make a new color shade. So to create a larger gamut with pigment inks, you need more color shades. You do not need the same color shades to make a similar gamut in dye inks. Matter of fact, 4 colors, which including black, in dye inks can make a greater color gamut in some areas than an 11-color pigment ink. In my experience, you need approximately 12 pigment inks to create the same color gamut or a similar color gamut to that of dye inks. If we have a look at this image that I had got courtesy of my friends at Mitsubishi, you'll see that we have a yellow droplet, a magenta droplet, and a cyan droplet. And I hope that your viewing device will allow you to see that it created blue where it overlapped. Over here we've got a cyan and a yellow, and where it overlapped we'll see green. And where we have yellow, magenta, and cyan dropped all on top of each other, we can now see that the color shade is a shade of gray. So I'm proving to you by electron microscope that indeed dye inks are translucent, and we can create new shades in the overlap. A little bit more of a visual, and I'm going to give just a wee bit of history how pigment inks expanded from a 4-color pigment ink system of cyan, magenta, yellow to multicolor. And it had to do with skin tones. When we started to make skin tones out of 4 shades with pigment inks, to warm or cool down the skin tones, we had to add cyan or magenta. When we added cyan, it's a very strong looking color shade, so we didn't want to add too many cyan droplets to cool down the skin tone. But because the droplets were quite large, we actually got to see a bit of a grainy image. So what they did is they created light cyan and light magenta. Therefore, we could put more droplets and reduce the grainy effect. Pigment inks tend to be more grainy than dye inks, just simply because of the droplet size and the clumping together. So to cool down this image, I've added light cyan. To warm up this image, I add light magenta. And that's generally how pigment inks are controlled as far as the color shades. Dye inks are quite different. Because they overlap, because when they overlap, they create a new shade, it's very easy to create the color tone that is required without additional color shades required. Because the droplet size is smaller, and because when they overlap they don't clump, we get a smoother gradation of skin tone and a lower grainy appearance. When it comes to color gamut, on the left-hand side here we have an 11-color pigment ink system, and on the right-hand side we have a 4-color Noritsu dye ink system. This gray line right here on both graphs is sRGB, and the overall color spectrum here is all the colors the human eye can see. So as you can see, neither of the systems can reproduce all the colors our eye are capable of seeing, but it does a very good rendition of exceeding sRGB in both cases. In the case of this 11-color pigment ink system, you can see that the green goes a little bit deeper into the lighter green areas. They're about equal in this deep blue area. However, the dye ink exceeds red and magenta significantly than the 11 ink pigment system. In fact, it is my experience that you need 12 pigment ink systems, 12 pigment ink colors to be able to match the color balance, the color gamut, of the Noritsu dye ink system. When we compare it to silver halide, again, this gray line is sRGB. The inside white line is silver halide, and the outside line here is the color gamut of the dye ink. So as we can see, the Noritsu dye ink system can create all the colors that silver halide can. In fact, it can create more. It can go deeper into magenta red and provide a greater range of skin tones. It goes a little bit deeper into the sky area and much deeper into the green. So in fact, the dye ink system are able to reproduce colors well beyond sRGB. Some people say to me they're more vibrant, they're richer, they're more contrasty, they're more saturated. If we printed an image of a white cow eating marshmallows in a snowstorm, the dye ink system will not print any colors at all. The dye ink system will only print the colors that the file has on it. It will not exaggerate the colors. It will not add colors. It will do as it's told from the file. So I do not agree that dye inks or inkjet technology whatsoever is more saturated. That would be the wrong term. If we had a gray print that had 100 gray shades of gray in between its white and its black, and we saturated that, we would make it more contrasty, and we would take shades of gray away. We do not do that in inkjet. We provide more shades, so we are not saturating the file at all with the print. We are printing what is on the file. If the information is there, the inkjet will print it. The software, if the software that's controlling the printer allows it. When people suggest to me that inkjet cannot create the same skin tone shade as silver halide, I do take exception to that, and I do carry around a set of sample prints. These images here are scanned from the sample prints themselves. So what we have on the left is a QSS37HD. That is a 36-bit printer. It had fresh paper and fresh chemistry. This is the best of a silver halide process and the skin tone that resulted from it. This print labeled HD Dry is from a D1005 using the inkjet profile, the Noritsu Coding -02, and I was able to create the exact same skin tone as I did in the silver halide paper. However, what also occurs is it is going to provide the colors that are on the file for green, magenta, red, etc. So when you look at the greens, when you look at the magentas, you will see a completely different shade in the inkjet gamut versus the silver halide gamut. The inkjet is not creating an imaginary shade. It is doing the shade that the file is telling it. It is creating the file that is telling it. However, as you saw in the graph earlier, the silver halide paper was not able to create that light green shade. So it went to a darker green shade. It rendered the file to a shade that it can reproduce. Which one is more accurate? I didn't see the person live, but based on my knowledge of inkjet technology and our software and how it's going to work, I believe that that shade of green is the accurate capture of that shade. as well as the magenta. Now we are at the mercy of your monitor. I know some of you are using a projector right now, and unless you're using a newer projector, those two shades of green may look the same to you. That is because of your monitor or your projector itself. Those of you who are using a better quality monitor right now, you are seeing the differences that I'm talking about. However, the Noritsu printer has the ability to print and render similar to a silver halide print. That printer profile that we provide ends with a -01, and it's designed to replicate silver halide color tones. The skin tone, once again, will be the same. It does not change the skin tone itself, but it does reduce the gamut of the inkjet to the similar gamut of silver halide. That being said, inkjet will never replicate silver halide because the paper base itself is brighter white and the blacks are created from black ink, whereas in silver halide the black is created by equal amount of cyan, magenta, and yellow dye. So the contrast range of inkjet technology will exceed, or does exceed, that of silver halide. As a result, we will not be able to replicate the exact look of silver halide, just a similar look with a greater contrast tonal range. One of the things that I think people object to in inkjet technology and skin tone versus silver halide is the fact that the skin tone on inkjet is more accurately replicated due to its replicated based on the information on the file due to the fact that inkjet is sharper than silver halide. This is a very close scan of those prints, the nose of the person. So you are looking on the right-hand side of the inkjet file, very accurately being portrayed by the inkjet printer technology. On the left-hand side, you do have the scanned silver halide print. So you can see the details within the file itself. The inkjet is not creating that information, it is printing it as it sees it on the file. But if we were to reduce the sharpness within the software program of inkjet and blur the image, note how the two of them have a very similar rendition now. So one of the objections between inkjet skin tone versus silver halide may have to do with the sharpness itself and less with the color itself. Sharpness for inkjet is controlled by feathering of the droplet. That technical term for that is the droplet dot gain. When the droplet comes out of the nozzle, it's very close to being round. The goal is to keep it as round as possible. As it drops down, it does have a very round appearance, but when it hits the paper, gravity is going to want to try to make it oval, and it's going to spread when it becomes oval. Notice how much wider the dot on the right is than the dot on the left. This is called dot gain in feathering, and it reduces sharpness of the image itself. Different papers have different dot gain. The amount of emulsion or absorption labor on the paper itself will impact the dot gain. There has to be enough absorption layer, that is the thickness itself of the absorption layer itself on the paper, so that the droplet has the ability to stay round and doesn't bottom out on the layer and get dot gain. So it's not just the printer and the technology itself that controls sharpness, the paper controls the sharpness as well. So as you can see, I have a very thick emulsion, the top coating of the inkjet paper, and we can demonstrate how the dot does feather. There is some feathering at all times. We want to reduce that feathering to increase the sharpness and the saturation of that droplet. The next topic I wish to talk about is inkjet printer resolution. It's a little bit confusing out there as people in the marketing world start to use numbers in different ways. And generally when we see a higher number, we think higher quality, sharper, and that as a rule of thumb is true. However, sometimes the resolution of a printer is described by the number of inks times the resolution of the head itself. That is, if we have a head that's capable of 150 dots per inch, and we have 4 colors, the marketing people may report this printer as a 600 DPI printer because we take 150 and multiply it by the 4 inks. That would not be a good way to determine if this is a high quality printer. What you need to know is the native resolution of the head itself. And as far as I know, in the imaging world, that is either 300 DPI or 360 DPI. There are not a lot of manufacturers of heads. There's very few, and the technology is licensed to other companies. My research tells me that there's only 300 dots per inch heads and 360 dot per inch heads. So then, what is a 720, 1440, and 2880 printer? Well, let's take the native resolution of a 360 dot per inch printer, and in this example, it's a QSS green. So when we look at the print, we talk about the x-axis and we talk about the y-axis. The x-axis is the travel of the head. The y-axis is the advance of the paper. The Noritsu printer in standard mode is a 720 by 720 printer because we have 2 heads. The making of an 8 by 10 takes approximately 1 minute on a QSS screen. We can put the printer into 1440 mode. When we do that, we utilize the smaller droplet sizes and no longer use the large ones. But because it takes a longer amount of time to put all those small droplets, we have to reduce the paper advance by 50%. And an 8 by 10 now takes 2 minutes to come out. We can also go into 1440 by 2880 mode. And although we use the same size droplets and the same amount of droplets, we'll reduce the paper speed again 25% and do a greater overlapping of the covering. And the 8 by 10 now takes approximately 4 minutes. Now, this is just an example, not real life. I've just used numbers to give it an idea of what happens to the printer when you use those different resolution modes. Please note that in all 3 cases, it is a 360 dot per inch printer. I do talk about the droplet size. In Noritsu, we do have the ability of 5 different droplet size. They start at 1.5 picoliters and they go up to approximately 14 picoliters. So when we need to drop a lot of ink and make a solid tone, we use a large droplet size. When we need to create fine detail around the eyelashes, we used a smaller droplet size. This is an image that I captured with using a microscope. And as you can see, this is from a Noritsu printer. This is the letter R. You can actually see how the black ink has created the solid part of the R, but it did want to create a little softer tone, so it did drop some colors around the edges so that it's not a harsh line onto the paper. And within that, you can actually see the small droplet size, the 1.5 picoliters. Now keep in mind, your human eye, even those of you with a young eye that do not need reading glasses, you still cannot see beyond 267 dot per inch. There is no direct ratio of picoliters to dot per inch because, as I mentioned, feathering, dot gain of the droplet size is dependent of the paper. So it would not be a fair comparison to say 1.5 picoliters is the equivalent of a certain DPI. But I will state that my research tells me that a 1.5 droplet of picoliter on standard RC high-quality microporous paper, such as we use at Noritsu, that would be the equivalent of about 700 to 800 DPI. That's pretty sharp. Excuse me there while I take a sip to wet my throat. Here's a file, very nice looking family portrait. I'm going to take this print and I'm going to scan it on the highest quality scanner I have available to me at the highest resolution setting. And I'm going to focus on that eye. There is the Noritsu in 720 by 720 mode, as well as in 14 by 40 mode. And we can see the smaller droplet size has created a smoother tone. And in the end result, increased sharpness. This is an 8 by 10 print that I typed some text on. And I just put some random numbers there so that I can enlarge that text so you can have a really close look and see what the droplet size is doing in the creation of that text itself. I purposely didn't use black. I used a grayish tone in the back, so you can see how grain is made up of all the different color dots, and as they overlap to create the new shape. Very similar file. Going back to the lady at the family picture, we can see how the droplets are forming to create the skin tone. Now, when the droplets get close together and clump together, that is when we can see the darker droplets versus the lighter ones. And that clumping is what we now see and call grain. The grain that we see in an image, or the graininess of an image, is not a drop. It is a clumping of drops. I'm going to enlarge it even further, and now you can see a clumping of the dots right there. And those clumping together is what creates the graininess of the print. The clumping of the dots is controlled by the software algorithms and the dithering program. Companies are constantly trying to improve their dithering algorithms to reduce this clumping effect and thus reduce the graininess of the image. However, the dot size itself is important, and remember that dye inks are capable of a smaller droplet size than pigment inks. So pigment inks are going to be more susceptible to a grainy image because their clumping will be more visible than that of the dye ink system. There are two types of papers. We have resin-coated paper and non-resin-coated paper. And within the non-resin-coated paper, there are a variety within them. However, with the resin-coated paper, we basically have traditional photo-grade paper. In the non-resin-coated, we have matte to provide a true matte look, art paper, which is used often to provide a texture in the paper. We have fine art and rag paper, which either is 100% cotton or has some cotton fiber in it. And then we have cast-coated paper, which is a traditional look for imaging prints before RC papers were created. So I'm going to expand on that a little bit further. Noritsu roll paper has a plastic resin, an RC coating on both sides of the paper base itself. That makes the paper water resistant. The ink absorption layer is then coated on top of the paper, created the emulsion or the absorption coat, depending on how you wish to call it. Printers such as the earlier Noritsu DDP series printer used polymer emulsion coating, emulsion layer, absorption layer, because the pinks are only partially absorbed into the emulsion and remain on top. The two bond together to create a new molecular structure. So pigment inks are more durable because the absorption layer and the ink itself bond to create a new structure that is much tougher than silver halide prints or dye inks. Dye inks use microporous paper, which the ink is absorbed into the emulsion itself, and the droplet is below the surface. This reduces drying time and increases abrasion resistance of the paper itself. Again, I mentioned that dye inks are more sensitive to abrasion. When you take your fingernail and rub it across a dye ink, you'll see a pressure mark. And that is because the ink is still on the surface, where some of the dye ink pigment ink remains on the surface of the print, whereas the dye ink, if the absorption layer is thick enough, will penetrate and go below the surface. RC paper can have a gloss, semi-gloss, or a luster surface, but it will not have a matte surface. It will always have a sheen of some sort. Because RC paper has a plastic layer between the absorption layer and the paper base, the ink will never reach the paper base. Non-resin paper falls into a few different areas, such as matte, art, and cast-coated paper. Matte paper has the absorption layer directly on top of the paper base itself. The ink can pass through the absorption layer and reach the paper fiber. And then when it reaches the paper fiber, it gets dot gain. When it gets dot gain, it loses some sharpness. Additionally, matte paper is more sensitive to abrasion. Just by the nature itself, it tends to be more sensitive to scratching. Art papers are generally acid-free in the making of the paper fiber itself. Originally, cotton was used to create an acid-free product. We don't want acid in the paper itself because acid reacts with the paper fiber over time and causes the paper to go yellow. So acid-free paper is requested by a lot of purists because they want to ensure that the paper does not yellow over time. The photographic paper manufactured by Noritsu is acid-free. The paper fiber itself is a cellulose tree fiber, but it's not bleached with acid. So it won't yellow over time, such as traditional papers have in the past, like a newspaper. Cast-coated paper was the type of technology used before the resin-coated paper came about. Cast-coated paper is where the paper manufacturing process treats one side of the paper with heat and pressure to tighten the bond between the fibers itself. This makes a more dense paper surface, and the ink is less likely to penetrate into the paper fiber. That reduces dot gain and creates for a sharper image. It also increases the sheen of the paper, so you don't get a matte cast-coated paper. So some of the attributes of RC paper are: it is the sharpest due to the lowest dot gain. Because the droplet stays round and together, it's the most vibrant in color. It's more water resistant. However, it is limited to luster, semi-gloss, and gloss. We're not going to get a matte paper. Matte paper will not cockle when it gets highly saturated with ink. Cockling is when the paper gets so much moisture absorbed into it that it actually contracts and wrinkles. RC paper is more resistant to abrasion as well. The advantage of a non-RC paper is it comes in a wide range of surface thicknesses and weights. There's a lot of specialty art papers and cotton papers that are non-RC. The disadvantage is it will cockle when it gets wet. So when it gets too saturated, it will wrinkle and bubble. That is why non-RC paper is not ideal for making duplex prints, because the second pass may have some cockling, and then the paper may strike the head in the second pass. So we want to use an RC paper when we're doing duplex printing. Non-RC paper is highly sensitive to surface abrasion as well. And when I mean abrasion, I don't necessarily mean a scratch, although that can definitely be an abrasion, but just when prints rub together, they make a little bit of a surface mark. Another term that is often used in inkjet is swellable paper. This is the polymer paper. And again, the ink and the paper, the ink and the emulsion layer bond together to create a new molecular structure, and it protects the ink from airborne contaminants such as ozone. So when we use a pigment ink with a polymer type paper, it does have the greatest etch permanence because the ink itself is protected. Porous paper is often referred to as an instant dry paper. It's not really dry, but the ink is below the surface and will not smudge or spread. It may not be dry, but it does allow us to have the paper touch the roller, roller after it's laid down very quickly, and the ink will not transfer to the roller because it's below the surface, assuming the absorption layer is thick enough. And that is why we use microporous paper in high-speed inkjet printing, such as the Noritsu 1005. It's a very fast printer, and therefore we have to use dye inks. One thing that's important to note that in all inkjet printing, both with swellable and porous paper, there is off-gassing for up to 24 hours. This off-gassing is the solvents drying, the carrier. So the liquid is drying and a gas is being emitted. As a result, it's important not to frame a print and seal the print within a frame behind glass, because the gas could put a coating on the glass that will be there forever until cleaned. And that will be a detrimental look to your glass framed print. So inkjet prints should not be framed within 24 hours unless we try to accelerate the off-gassing. And one way to do that is to put a regular piece of white bond paper, that bond meaning like photocopy paper, just lay that on top of the print, let it come in contact with the emulsion, and will act like a sponge, and it will accelerate the off-gassing. It's my understanding that it can accelerate it so that all the off-gassing is done, even as low as within 2 hours. I've talked quite a bit about the absorption layer. The top coating in emulsion in terms is absorption layer. Because I tend to use photo terms, a lot of us in the industry call it the emulsion, when indeed it truly is the absorption layer. The microporous layer is like a sponge. Now, we never want a sponge to dry out completely, but a sponge is rather useless to us if it's completely soaking wet. So we do want some moisture in the sponge, and we do want some moisture within the microporous layer. When the paper is manufactured, it's manufactured under very strict humidity controls to control about the amount of moisture within the emulsion itself. It's then sealed in a plastic bag. So it's very important that the paper be left in the plastic bag right up until its use. The area of which the paper is being used and the printer should be in a controlled, humidity-controlled environment. If the humidity is too high and the paper is left sitting, the outside surface of the paper will absorb the moisture in the air just like a sponge will do. If too much moisture is absorbed by the paper, then there's no room for the ink, and the ink may not penetrate deep enough into the absorption layer and may be onto the surface. That could cause smudging and marks onto the rollers as it transports through the printer. However, one of the disadvantages of a microporous layer is paper is it squeaks. I think everybody has heard this here. You've probably wondered why some paper squeaks and some paper doesn't. And that's got to do with the fact that the absorption layer will pull out any liquid or lubricant between what it's touching and its emulsion. And without the lubricant, you get a squeaky sound. So the microporous paper does squeak, and there's no two ways about it. The polymer absorption layer acts like a glue, like a part A and part B glue, and it bonds together to create a whole new substance. It's more resistance to tearing and its abrasion resistance. It's more light fast. It requires a longer drying time, so using it in fast printing is very difficult. I'm going to bring up all 4 different papers here, and I'm going to start with the microporous paper. Here we have the RC coating, the paper fiber itself, the other RC coating, and here's our absorption layer. The droplet comes down, and as it passes through, you can see that it's going to penetrate and make a block of ink. And hopefully, the dot gain will not exceed the width of the droplet itself. When we look at the RC paper, we can see that the droplet does penetrate into the emulsion layer. However, some of the droplet remains on the surface, as I've been mentioning to you. When we go to the matte paper, we don't have any protective coating between the absorption layer and the paper fiber. So we do get some dot gain when the droplet reaches the paper fiber. That dot gain will be seen as a reduction in sharpness. And that's why cast-coated paper was created. When the paper fiber itself was manufactured, heat and pressure was used to create a tighter bond of the paper fiber to reduce the dot gain. So cast-coated paper is sharper than the matte and the art paper, but not as sharp as an RC paper. And that's strictly due to the dot gain. Courtesy of our friends at Mitsubishi, they provided me these images from an electron microscope. And as we can see, we have plain paper where the dot is feathering and get some dot gain. We've got cast-coated paper where the density of the paper is much greater here, and the dot gain is reduced. And then we have RC paper, and you can see that the dot is very, very tight. What does that mean for sharpness? Well, it's quite evident in this images here. We can clearly see the dot gain, loss of sharpness, improved in the cast-coated paper, and a very clear tight dot in the RC paper. And that simply is why RC paper is sharper than all the other papers on the market. recording. Paper thickness and weight is quite important. There is no correlation between the weight or the thickness of the paper. They are completely different representations of the product. Thickness could also be referred to as caliper. In North America, we tend to use mils to identify the thickness of the paper, and photographic paper tends to be 9 or 10 mil. Traditional photo silver halide paper was 9 mil, and Noritsu utilizes a 9 mil inkjet paper. We do talk about the weight of the paper in pounds or grams per square meter. The term pounds tends to be used when we're talking about a non-imaging paper, such as a photocopier paper. Then they would talk about the weight or the pounds of the paper. We don't really talk too much about the weight of the paper in silver halide, in inkjet. We're more concerned with the thickness of the paper itself. But I have learned by experience that utilizing a paper within the Noritsu QSS Green 1 series, the weight of the paper can go as high as about 320 grams per square meter. And then the rigidity of the paper tends to be an impeding factor of it transporting properly through the equipment. The images on the bottom, we can see we have a paper at 350 grams per square meter, and it's 14 mil thick. And we have another paper that's 250 grams per meter, and it's 10 mil thick. Again, there's no correlation between the weight and the thickness of the paper, although sometimes with experience, you can use the two numbers together to get a good idea of what that paper is like just by reading the specifications. If I do take a paper, such as this image here shown on the right and the left, of 250 grams per square meter and 16 millimeter, and I create a denser paper fiber, that term of creating a denser paper fiber is called calendering. And we have a wide variety of different art papers that are calendared to create a different look or feel. And again, calendering is creating a higher density within the paper fiber. When we calendar it, the paper can become thicker. So you notice that after I calendar this paper, they are both 250 grams per square meter, but now look at the difference in the thickness. And this is why you can't strictly go by the weight of the paper to determine its thickness. You can look at the weight and thickness of the paper and get a pretty good idea of its rigidity. And the paper on the right will be more rigid than the paper on the left. Paper manufacturers, when we're talking about buying commercial sheet paper in packages, generally will provide the information in weight or thickness. Rarely have I seen both on the packaging. I would like to know both. This will give me a much better indication of this paper if it's going to be successfully passed through a Noritsu Green printer. I've now got a very good feel for what the weight or the thickness of the paper is and whether it's going to be successful. And sometimes that just takes a lot of printing and experience before you get it. And I've done a lot of testing on QSS Green, so I've got a bit of that sensation of being able to pick up the feeling, touching the paper and touch and feel it, and get a really good indicator. However, there's nothing better than numbers. Noritsu uses the term ultra thin, thin, thick, and ultra thick to describe the thickness of its paper. And in those description of the paper, here's what we mean by the actual measurement of the paper. So I'm providing it to you in three ways. I'm providing it in millimeters, in microns, and in mils, which mil is not a metric term, it's a thousandth of an inch. And what we refer to as a thin paper is 9 mil, and that's the general thickness of a photographic paper used traditionally for a very long time. Notice the two images on the left are now both 10 mil paper. However, one of them is 250 grams per square meter and the other is 350 grams per square meter. because it was a thicker paper that was calendared during the milling process. This paper, that even though it's 10 mil, I know by experience will not pass through a QSS screen. I've yet to find a 350 gram per square meter that has a lower rigidity, a low enough rigidity to make all the tight turns required to pass through the printer. The coloring process is simply during the milling of the paper, pressure and heat is used to create a more denser paper. Generally speaking, they use the heat only on one side so that there's a greater calendaring effect on one side of the paper. And again, that is where the emulsion is going to be applied to reduce dot gain. So the paper usually has a higher density on one side than in the other side. And even though you buy this paper and it's not RC, it will still say which is the emulsion side, because the coating will only be put on one side of the paper. If you do use it the other way, you are putting the ink directly onto the paper fiber, and your result is not going to be as good as using the emulsion side. And hopefully you don't make a mess in your printer in the process. In Noritsu, we use 9 mil roll paper. We have successfully utilized 10 mil paper in our QSS green series. Even though 9 mil and 10 mil is only 10% difference in thickness itself, you can actually feel the difference in the paper. And I don't mean feel in the sense that I can measure the difference with my fingertips, but you can feel it in rigidity of the paper. The 10 mil paper has more rigidity to it than the 9 mil paper. We have experienced successfully in Canada and US using a metallic pearlescent paper that is 10 mil. However, it's important to understand when you use a thicker paper, and certainly when you start using a metallic paper, that it could be a little tougher on the cutter blades themselves. In the case of the metallic paper, or more accurately, we should use the term pearlescent paper because there isn't any metallic in it at all, it uses glass fibers. So to cut the paper, we are cutting through glass fibers. And as you can imagine, cutting glass with a sharp knife will probably dull it a little quicker than cutting through regular paper. Because we're cutting through these glass particles, sometimes the glass tears off the surface instead of a clean cut. My experience has shown that when we do a double cut from roll paper on a QSS screen, the first cut is a clean cut because of the tension of the paper. But because we're doing the second cut only a few millimeters apart, there isn't enough as much tension on the paper itself. So there is a little bit of a slippage of the knife, and we do get a little tearing effect of the emulsion. The emulsion or the absorption layer that has the glass particles will tear off slightly off the paper surface. If we lay that paper on a white background, we will probably not see it. But if we lay that edge on a black surface, we will then start to see the little bit of a tearing. So it will not be possible to get a good clean cut on pearlescent paper on a QSS screen unless you go into a single cut mode. Something else that you need to know about paper itself is the brightness and opacity of the paper. Brightness is a measurement of the amount of light that will be reflected off the white, the non-ink area of the paper, with 100 being 100% of the light reflected, such as in a mirror. Photo papers will have a rating of approximately 95 or slightly higher. Papers below 95 will have a very low reflectance and therefore not nearly as bright in its white appearance. Opacity is extremely important, particularly in duplex printing. When we're going to be printing on both sides, we don't want to see one image from the other side of the print. That would be very detrimental to the appearance of the print. So we need an opacity rating of about 94 or higher. When we're doing simplex printing or single-side printing, it's important that we still do not have a very low opacity number, because if we're using a back printer, a CVP, we don't want to see that back printing from the other side. If the end user decides to use a felt pen and write on the back of the print, they're going to be very disappointed if they can see their felt pen writing. So in photo paper, we want a high opacity rating. So when you're selecting your commercial sheet party paper, third-party sheet paper, you want to select a brightness that's about 95 or higher and an opacity of 94 or higher, and then you've got a very good photographic paper. Often the manufacturers use a term to describe the whiteness of its paper. There is no standard in this description. So when one manufacturer uses the term bright white, that does not mean another manufacturer's bright white is identical. There is no standard in that area. OBAs, optical brightness agents. It's very important that we understand what optical brightness agents are and the impact of the image itself when we're viewing it. An optical brightness agent is added during the milling of the paper or within the absorption layer itself. Its simple goal is to absorb all the UV light that's available to it and re-emit it as a blue light. In the process, it creates a brighter white and a brighter image, but it does cool down the image itself. Natural papers tend to have less OBAs, whereas a bright white paper will have more OBAs within it. OBAs fade faster than inks. So if left out in exposure to daylight, the OBA will fade much faster than the print. So over time, the brightness of the image itself will reduce if a lot of OBAs are used in the paper itself. I did mention to you that we do have a terminology such as bluish white, bright white, and yellowish white. While this image I've created here is an extreme exaggeration, I'm trying to give you an idea what we mean by a warm white or what we mean by a cool white when we talk about it in photographic terms. But a bright white does not necessarily mean the same thing on each manufacturer. The optical brightener can be used in two different ways. We can put the optical brightener within the absorption layer on top of the paper. Now we can see the optical brightener on the left-hand side creating a cooler white shade, whereas without an optical brightener, we have a warmer shade on the top. Or we can mill it directly into the paper and change the look of the paper fiber. This is the preferred process. But please keep in mind there are very few manufacturers manufacturers milling photographic paper. You can count them all on one hand and still have fingers to spare. So the amount of manufactured paper where the paper base is milled is very low. Noritsu paper optical brighteners are milled into the paper itself and not coated on top. But when you are buying third-party sheet papers, generally speaking, they did not mill their own paper. I should expand my earlier comment when I said photographic paper. When I do mean photographic paper, I am referring to RC paper. There are a lot of companies, manufacturers milling their own non-RC paper, but very few milling RC paper itself. Now, the method, the application of the OBAs do affect the way that the print will be viewed by ambient light and the permanence of the OBA within the image itself. I'm going to show you two different papers here. I'm going to show you Hahnemuhle and Canson. Under no way am I recommending or not recommending one paper or the other. I am simply just taking their sample sheets that they've provided to me, and I'm going to show you some differences within the paper. I do not mean that to be representative as a good or a bad thing. I'm just trying to show you the differences within their paper itself. So this is not an endorsement of one product over the other. In the case of the Hahnemuhle, I'm going to shine a black light onto the papers. This is my black light shining onto the papers, and I have photographed this with my Nikon D7000 camera. Now we can see the optical brighteners that Hahnemuhle is using in the paper. We can see that in their bright white, they're using some optical brighteners. In their cotton paper, it appears that they are still using a little bit of optical brighteners, but not very many. My guess is it's probably milled into the cotton paper itself. We could see in their bright white paper that there's more optical brighteners here. And the Burita paper itself also has similar optical brighteners. Hahnemuhle openly states that they do use optical brighteners. They don't try to hide this. They clearly document it and put in their specifications. And I compliment them for identifying that and making the consumer aware if they would like to be aware. Here's two different papers from Hahnemuhle, their fine art paper and their photo paper. And we can clearly see their photo grade paper has more optical brighteners in it. And that's because in the photo world, we want a brighter white. So to create that brighter white, much like we want a wedding dress to be the brightest thing in the church, we add optical brighteners. And just like a wedding dress, during the manufacturing of the material itself, they add optical brighteners to the wedding dress so that the UV light available will reflect more light, and that dress will be the whitest thing in the church. And for those of you who are using film many, many years ago and capturing weddings, you've often found it was very difficult to get the wedding dress to be clean white. It often had a cyan color, and that was because of the optical brighteners creating a cyan color capture because film is sensitive to UV. So I detract a little bit, but thought I'd throw that bit of information in. I'm going to show you a sample print from Hahnemuhle photographic paper. And this sample print I had sitting near my window in my home office. And on top of the print itself, there was another piece of paper covering this area of the print. So this area here was exposed to sunlight for approximately 2 months before I started to notice a difference in the look of the white. And in 2 months, the OBA faded on the Hahnemuhle paper. And when I had UV light available to me, I was able to see that within the paper itself. But if I had no UV light, the paper looked absolutely fine, as it did here. So illumination of the print itself became a very important factor. And that led me down a path on a completely different presentation, which I'm going to go to shortly. Canson does identify which of their papers are OBA free and which are not, clearly on their packaging. Now, Hahnemuhle does identify it as well too. Canson tends to promote a little bit more than Hahnemuhle their products that are OBA free. And we could see that indeed this paper that they say is OBA free probably does not have any optical brighteners in it, because when I shine that black light on there, the UV light, I do not get very much reflectance. And we can see that their photo grade paper is highly reflective. So indeed they have a lot of optical brighteners in their photo paper. Their Burita paper is much lower in optical brighteners than I would have expected. As I talked about earlier, the illumination of the print and the image itself is extremely important to how the print is going to actually look. And what I mean by illumination is the light source. Fluorescent technology utilizes UV light. When we have a fluorescent tube, it creates UV light. The powder within the bulb itself, or the tube, collects that UV light and re-emits it as a visible light. But it still transmits a lot of UV light. Now, it doesn't transmit the dangerous UV lights into the... What just happened here? Pardon me. It does not transmit dangerous UV light, which is down in the 200 to 300 area, but it does transmit some visible UV light in the 300 and 400 wavelength nanometer area. So when we're viewing an inkjet print with optical brighteners, it will look different in fluorescent light than it will in some other lightings that does not have as much UV light. Even though we talk about a high quality fixture having 5,000 degree Kelvin, it's important to understand there is still a lot of UV light being transmitted from that fixture itself. I should also note that silver halide papers also had optical brighteners in them. Those optical brighteners were usually used in the milling of the paper, not in the coating. If we were to take the silver halide paper and an inkjet paper and look under daylight, they will look identical. But when we start to throw out mixed color lighting such as that as fluorescent, we can start to see a difference between the two papers themselves. And that's because of the optical brighteners that would be used in silver halide or inkjet paper. Just going to skip through that and get to the next topic, which is the inks. There are two types of black inks that are used. We have photo black ink and matte black ink. They are never used at the same time. Photo black ink is designed for RC papers, whereas matte black is designed for non-RC papers. And the purpose of the two inks is to create as deep a black as possible while reducing the negative impact of being absorbed incorrectly into the emulsion. Printers often have the ability to accept both photo black and matte black, but they are never used at the same time. When the printer has the capability of taking both blacks, when a paper is set up in that printer, it's indicated whether it's a matte paper or a non-matte paper, or non-RC paper. And that's where the printer will decide which ink will be utilized. If the wrong ink is used, it's not going to be detrimental to the quality and the permanence, but it will impact how deep of a black that will be presented within the paper itself, or the image itself. We have the term glossy, we have the term semi-gloss, which is very similar to luster. Semi-gloss has a slight more of a sheen than when the term luster is used. And then, of course, we have true matte. And what we mean by true matte is a true matte surface that has very little sheen to it. And the difference between these papers is just simply the manner of which they reflect light. Either they reflect a lot of light, the light scatters, or the light scatters a lot more. And again, just want to emphasize that semi-gloss and luster often look very similar. Side by side, semi-gloss tends to have just a wee bit more of a sheen than a luster surface will look. The luster will have a little bit more of a tooth, as it's called. I did talk about acid paper. Acid is used to bleach the paper base itself during manufacture. And again, as I mentioned, when the acid is within the paper fiber and exposed to light, it will yellow fairly quickly. But even if not exposed to light, the acid within the paper fiber can cause the paper to yellow over time. Fine art papers were created first because of the use of cotton cellulose, which is pH neutral when it's manufactured. So it had no acid and tends not to yet color or disfigure as time goes by. Please be aware that there is a difference between fine art and art papers. Art papers are likely cellulose paper that may or may not be pH neutral. Fine art papers usually are pH neutral, usually 100% rag or cotton cellulose. And again, art papers will have some wood cellulose in it. They may have some cotton in it, but generally they're wood cellulose, and they're usually not acid-free. And again, RC paper, such as Noritsu paper, is manufactured with an alkaline process, keeping it acid-free. Burita papers are traditionally used for black and white printing. Although you can print color on Burita papers, they are designed for black and white. They use the element barite to make a barium sulfide product. And it's been used for a very, very long time, since the early era of inkjet technology. They may be used with or without OBAs, but I'll tell you, they do create a very nice look, feel, texture, and a nice deep black that other papers tend not to do. They really are ideal for black and white. A fiber paper is often used as a term to describe Burita paper. That is because traditional fiber papers were Burita paper. Burita papers generally tend to be a warmer tone and don't use optical brighteners. So you won't get as bright of a white, but you will get a very deep black. The next area I'd like to talk about is banding. There are three types of banding in our photo world. One is the mechanical banding, which we almost always refer to as banding within the print. That's a light or a dark band that is equally spaced within the print itself. The image I'm showing as an example here, I created for this presentation purposes, so I'm emphasizing the banding. The banding is caused because the paper advance and the head transportation is not synchronized, and that is what causes the banding. The reason for a dark band is when the paper path width of the ink being sprayed down overlaps with the next path, and that overlap causes a dark band. But if the paper advance is greater than it should be, then the one path does not butt up against the original path, and we get a lighter band. To reduce banding, we try to spray the ink in many passes over the same area, and that in its sense reduces banding. Home printers tend not to do that. One pass is the pass, and as a result, home printers tend to be more susceptible to showing banding than commercial printers. Color depth banding is something completely different, yet I sometimes have examples brought to me that indicate that their printer is banding. But it isn't in this particular case. This is banding within the file. And banding is often caused in Photoshop when users, particularly with sky shots, increase their saturation. And the file creates this color depth banding. And color depth banding is easily identified because it's usually curved. It's very rarely in a straight line. And as those of you who are familiar with how an inkjet printer works, it's not going to create a curved banding line. So this is color depth banding. Now, sometimes I've had people print this on a silver halide print, and it indicate, they'll say, see, it's not on a silver halide print. And that's because a silver halide printer itself is not as sharp as an inkjet printer. So it doesn't have the ability of showing you the banding. The banding's within the file, but the inkjet print itself, because of the mere nature of the way it works, may not show that banding. So some people who are adjusting their files and adjusting the saturation to print on a Noritsu QSS and are very used to the results of how they're created, may use the exact same file on an inkjet printer and see the banding and think there is something wrong with the printer, when there is nothing wrong with the printer. The file has color depth banding. So the way that the image is processed in Photoshop should be or could be a little bit different for inkjet versus silver halide. The last form of banding could be caused by clogged nozzles, and those are very easily identified by very narrow, thin, white lines. And that is a plug nozzle that just requires usually a good head cleaning, and hopefully nothing more than that. Now I'm going to just give you a little bit more of a visual of mechanical banding. When the spray comes out of the nozzle, it does have a connular shape to it. It's not a direct straight line. And of course, for this image purposes for this presentation, I am exaggerating that look. Here is one pass right there, the first pass of the nozzle, and now we have the second pass of the nozzle. And you can see where it's overlapped here, we're going to get a dark band. What we need to do is to increase the paper advance so that that line of that cone lines up with this cone, and therefore we eliminate the banding. Or we can adjust the platen. The platen is the gap between the paper deck itself and the surface. In this example, the platen gap is being adjusted by using a thicker paper. Now the QSS Green 1 actually has an adjustable platen gap, and that is because we can reduce the amount of mechanical adjustment that is required to eliminate banding. But if we do put a thicker paper in, we are coming closer to the head and reducing the width of the cone. So while we got a thinner paper here and a dark band, we could now get a light band over here because our mechanical adjustment is not correct. So we have to reduce the paper advance so that that area and that area lines up quite clearly. And that is the best that I could do in explaining the causes and the corrections for mechanical banding on a printer. I'm going to start it. This next section I'm going to talk to you about is the importance of illumination when viewing prints or even capturing images. I learned over time that whether we had a tungsten light bulb or a fluorescent light bulb and recently an LED light bulb, I've noticed that the prints started to look very different under the different light sources. So I studied this very closely, and I wrote a white paper that was published by the International Science and Technology Symposium. And this white paper was very well received. It appears that I hit a topic that hadn't been identified before in image viewing. So what I'm going to go through right now is something that you're not going to find a lot of information out in any of your searches. I was fortunate enough to receive some training because Noritsu acquired a LED light manufacturing company in Japan, and I had the opportunity to go there and be trained by the engineers themselves. So I learned a lot about LED lighting and illumination in general. Taking that information with my knowledge of imaging, I was able to combine the two and answer some questions out there that have been puzzling me and other people for quite some time. And that is, why does a fluorescent bulb, a 5,000 degree Kelvin, a daylight bulb, two different bulbs themselves produce two different looks? So here I have a bulb on the left that's producing a very nice image and a bulb on the right that's producing a cool image. Yet both of these bulbs are 5,000 degree Kelvin, but by two different manufacturers. And what I learned is when I went into the specifications of the bulb, this bulb had a CRI number, which stands for Color Rendering Index of 92. This bulb had a Color Rendering Index of 80. The target is 100, with 100 being perfect. This bulb came within 92 points of achieving 5,000 degree Kelvin. This bulb at 80 did not achieve 5,000 degree Kelvin. They sell it as a 5,000 degree Kelvin because that's their target. But by putting the disclaimer CRI 80, they are identifying we didn't get very close to the target. A CRI number of approximately 95 or higher is fantastic. If you get into the 90s, you are getting a very good quality bulb. I'm going to expand on that a little bit further. But what I got really puzzled about when I understood that was this. Why did this halogen bulb at a CRI of 98 look yellow and horrible to me, while this fluorescent bulb had a CRI of 83, although not perfect, had a better skin tone? And that's because I learned part 2 of the color rendering index. You have to know what the target is. Once you can find out what their target was, I found out that this bulb targeted 5,000 degree Kelvin and it got to 83. It's trying to produce 5,000 degree Kelvin, quite a bit from it, but this bulb was trying to reproduce 3,200 degrees Kelvin, a very warm light, and it got very close to achieving that. That is not the bulb I want. So you can't go by rendering index itself. You want the rendering index and the target. The two pieces of information together tells you a lot about the illumination device. I'm going to back up a wee bit, then I'm going to come back to that topic. I think it's important that we remember back to the archives. We always have to remember history so we don't repeat it. I'm going to talk about film just briefly here. Film was never designed to reproduce color the way it is. It was designed to reproduce color the way we remembered it. Kodak, Agfa, Konica, and Fuji all spent a great deal of time in studied groups and tried to recreate colors the way people think they were. But eventually Fuji came out with a film that was called Reala. And Reala film was designed to reproduce colors much more accurately. And that film was very well received, to the point that they eventually incorporated that technology within their standard film. And film became a lot more accurate. And this film was very good, but it was right on the beginning of the digital revolution, and digital cameras started to come out. But again, remember, when we had film, we had two color temperatures. We had indoor and outdoor film. And that was mainly because we had tungsten or daylight lighting. There was only two types of lighting on the market. But over time, we got tungsten lighting, we got fluorescent lighting, and then we got a whole bunch more of different lightings. So we would take our incandescent film designed for a light bulb and try to shoot under fluorescent, and it looked terrible. and we'd shoot under mercury vapor and under sodium vapor, and we got terrible results. We needed more and more different types of film. But the digital revolution was starting, and we didn't need to create more films because the camera itself had the ability to try to adapt. There's a lot of wonderful features in digital cameras. We've got larger, better dynamic range sensors with adjustable ISOs and auto white balancing to adjust for those different light sources. The flashes became automatic and adjusted quite nicely. Then LED flashes started to come out, and that's created an interesting phenomenon that I'm going to expand on. As well as the fact that the sensors are so good at shooting in low light, we often don't turn the flash on anymore. And that in itself is creating some challenges for us in the imaging world. We've often seen a case where generally an older gentleman is walking around with a blue sock and a white sock, and I fit the category of older gentleman. I've done this myself. And that is because the socks were either taken out of their drawer or paired under tungsten lighting. Tungsten lighting has very low blue light. So it's very easy to mix up a blue sock and a black sock because blue will look black under tungsten lighting. But if we look at those two socks under full spectrum, such as outdoors, we clearly see that there's the blue sock and the black sock. Although an extreme exaggeration of my point, this phenomenon occurs in inkjet prints. And there will be an impact on how shades are viewed and seen under different lighting technologies. Metamerism is when we have two color shades that look identical in one lighting source and completely different in another source. And because we have inkjet dye sublimation and silver halide prints on the market, they each have their different effect on metamerism. Whereas a traditional print made with color paper, and I'm using a black and white image here, may have a magenta cast, that very same image on inkjet could have a bluish cast because of all the UV light being provided out of the fluorescent light fixture. When we have image capture, we also have a similar phenomenon. Even though we have the auto white adjustment of the camera, there still was not the same color available in this lighting to create an accurate rendition of the subject. Yet we've got to try to print that image, that capture, to look like this. That is what the end user is going to expect. And it's usually not possible. I'd like to show you two different fluorescent bulbs. We have the green line, which is representing one fluorescent bulb, and we have a red line that's reflecting a higher quality fluorescent bulb. Notice the peaks and valleys in these bulbs. It's not a continuous even tone of all colors. However, LED, although it does have some peaks and valleys, LED tends to be a little bit more continuous in its white light output. But also important is this. Fluorescent light and virtually all light sources, except LED, do transmit UV light. Now look at the UV light of these two fluorescent sources. Now look at the light here for the LED. It cuts off. So LED, unless designed to do so, does not have any UV light. Now remember why I spent so much time talking earlier about optical brighteners. Utilize UV light to give a brighter look on the print. And this is where I'm trying to put it all together for you. An inkjet print will have a different white and a different look under LED light than it will outdoors or under a fluorescent light source. Sunlight has a high level of UV light. Fluorescent lamps work by creating UV light and converting them to a red, green, blue wavelength. LED light does not emit any UV. Almost all light sources emit some infrared, and here's the important part. CMOS sensors capture UV and infrared light. So now the image capture itself is affected by the lighting conditions, whether they have UV light or not. Some cameras automatically set their white point at 6,500 degrees, but I have no evidence that that's a standard. I truly cannot find out what the auto white point setting is as a goal for any particular manufacturer, so I have to make the assumption that it's 6,500 degrees. Some cameras allow me to shift that by selecting tungsten, fluorescent, or a warm white, and I can shift the white point into a warmer tone. Or some cameras allow me to actually manually adjust the white point and create my own shade. I like Ken Rockwell, and I like this website. If you're not familiar with him, Ken Rockwell talks about imaging in general, camera hardware, and particularly Nikon. And what he taught me was the use of auto white balance versus manually setting the camera according to the light source. And what I learned from him, I practiced and found out that it is of my best interest to select the white source if the light source, if the camera offers it. And you will get a much more accurate and better rendition of the true colors that were available to it. While setting a white point is all fine and dandy in theory, this is my example to show you under extreme conditions that there is no way you can reproduce color accurately if the colors were not available in the light source itself. So here I have a sodium vapor light source shot at night. We know those trees are dark green. We know this pavement should be gray. No matter what I do in Photoshop, no matter what I do in a setting, I am not going to get dark tree greens and the gray concrete. Certainly not both at the same time. So unless the illumination has the colors I require in it, I will not be able to accurately record them. Color rendering index is a tool to provide you with the information required whether the light source has all of the colors of its target value. If its target value is 5500, we can see that this light source, sun, did a very good job at achieving its target value, whereas this 2700 degree Kelvin light bulb has a very low RA, or color rendering index value, of 50. It did not do a good job at recreating the color patches. These are the actual color patches used, by the way, to determine a color rendering index. To determine degrees Kelvin, we actually heat a black body up, and the color that the black body, such as a piece of carbon, glows determines what the color shade is, and therefore the temperature in Celsius, the color is recorded and provided to you as a color shade in degree Kelvin. If our target is 2700 degrees, that very same bulb will have an RA value of 100 because it achieved the 2700 degrees Kelvin target. And as per the example I have here, I'm showing you an image capture under different light sources. And under the two light sources of 3000 degree Kelvin, we can see two different bulbs providing a different color rendering index. And you can see that actually when we got to the higher color rendering index value, it starts to look very nice. Now here is a 6500 degree light source that has a very low color rendering index, and although looking at the image by itself it looks fine, it does definitely look on the cooler side. I would like to show you two different a lot of different light sources, but two different columns. The two columns highlighted in red is what I'd like you to have a look at. Here's a variety of different light sources, including the Noritsu's LED light source, and here is the rendering index that they're going to produce for a target of 5000 degree Kelvin. And as you can see, incandescent light, a light bulb does a very poor job. Sodium vapor, again, does a very poor job. But then look at the metal highlight produces a very nice job, as low voltage halogen as well too. Very good rendering index. High efficiency fluorescent lighting can produce good rendering index. 80 is a bit on the low side, but 90 is a very good rendering index. And notice that the LED lighting has a very high quality index. LED lighting has the best potential for creating a good quality white light balance. However, it does not have any UV light. Using an auto white balance in a tungsten light, notice how this capture is quite warm and quite appealing. Yet this auto white balance on the very same capture device created a cool balance. And now here's the very same capture device recording a different skin tone where the tungsten is not very good and the outdoor white balance is very good. The point here is that auto white balance can be somewhat inconsistent. It can do a great job at one point and it can do a terrible job at the next point, as I'm going to demonstrate to you here. This is my image. I shot 2 images. I am handheld. I did not use a tripod, and I tried to line up the 2 images. You can see at this broken tree, it's out a little bit in the alignment, but it gives you the point that I'd like to show you. Here, I use the auto white balance on my Nikon D7000, and I got a very cool image. Whereas it was a cloudy day, so I went into the settings and I changed the white balance to cloudy. And look at the difference in the color I was able to produce. These 2 images are pasted together and untouched in Photoshop. This is the image capture itself. When I did this image, it convinced me to no longer use auto white balance in my camera. And I now set the white balance as the scene changes. This is sometimes a little frustrating because the sun's out one time when I'm shooting and it goes behind a cloud and it's cloudy, and I do change the setting. Sometimes I forget, and that doesn't mean I get a bad image, but I get a better image now than I do using auto white balance setting. Just to bring it home and close off this session, I just want to talk a little bit more about the LED lighting. Here's an LED light fixture manufactured by Noritsu. This particular fixture is a 5,000 degree Kelvin, and its RA value is 85. So it's pretty good, but not really good at achieving 5,000 degree Kelvin. Here is a very high quality fixture with Octron 5,000 degree bulbs rated at 78. These 2 fixtures were side by side in a Noritsu demo room, and this is how I captured them, exactly like this with my Nikon D7000. I put the camera into daylight setting so that it is expecting white daylight. And as we can see, the image capture was quite clean on the LED, and now we start to see those cooler green tones that fluorescent light is famous for. These 2 images, although I showed them to you separately, they were shot at exactly the same time. I cut the 2 images apart in Photoshop for the visual effect. But that is exactly how they were captured. So this is demonstrating to me how LED lighting is going to produce a much cleaner light than even the best of the fluorescent bulbs can do. A little bit more of an example on that, just using a typical LED light to light up some color sources. Hopefully your viewing device will show you that the yellow and the red on the apple are much more saturated in its color rendition than out of the tungsten bulb. And if we bring a fluorescent bulb, it becomes even worse. An LED light is a pretty good capture device. But remember, the LED light does not have any UV light. So when we're viewing the print, it could be a very different impact on the fluorescent light than it was on the UV light. And certainly with sodium vapor viewing, it's an extreme. It looks absolutely horrible. Which takes me to this section. I took 5 different inkjet papers. Here are your 5 different inkjet papers, just labeled A, B, C, D. I captured them, I put them under daylight, and I took a picture with my Nikon D7000. Then I went under a street light, such as over here, and I captured them again. And look at the tone that I started to see in these different papers, which I could not see because of the optical brighteners. The sodium vapor does have very little UV light, so I'm now starting to see the true tone of the paper without the UV effect of the optical brighteners. The information on the right is just the technical data to support exactly how I created that imaging. And in conclusion, I just want to mention to you that LED light is emerging very quickly as the preferred lighting sources, mainly due to reduced energy consumption. However, it is a very high quality light source in its color rendition of red, green, blue. The disadvantage for us in the imaging world is it doesn't have any UV light, and the optical brighteners that we have will be underutilized in the viewing of the print. I have no solution on what we can do about this, and I'm just trying to create awareness to everybody. And on that note, that brings me to the end of the session. I thank everybody very much for staying online and attentive, and I hope you got information that is useful to you and your market. I'm going to stop the recording now and open up